Nice to meet you all. I'm one of Mario brothers. Oh, sorry, I'm Dmitry Chuyko from Bellsoft. And we are going to talk about ARM servers and how Java is great there. Because many people discuss moving to such new hardware, and we'll see how there are some clear reasons in doing that. I worked in Bellsoft, and in Bellsoft we produce our own OpenJDK distribution called Liberica JDK. You probably have heard about it if you used containers in Spring Boot, because you can build a container image, and inside that container image there's a JDK, and this is Liberica actually. And we also release our Linux for containers, but not only for containers. It's called Alpaquita. Maybe you've heard about it as well. And that's how we develop OpenJDK with other companies who participate in OpenJDK development. We invest in this cool open source project, and we do it for a long time. Like I previously worked at Oracle, and many of my colleagues worked at Sun Microsystems, so we're not just newcomers here. So let's get back to that ARM devices. We're all familiar with some small devices, IoT, or mobile phones, or tablets. You see how fast things change over the time. So this picture is like a few years old already, maybe 2 years or 3 years old. And all hardware here is oldish, right? In your pockets, all phones look differently. And the same is true for the internals, not just to how they look, but the hardware, hearts of the hardware, chipsets, systems on chip, CPUs, cores themselves, they are now much more powerful, much more interesting, and they power up real server hardware. Because most people who I talk to here work in a backend domain, right? Anyone not doing backend here? All right, what do you do? Like graphical applications, desktop?
Full stack.
Full stack, okay. Full stack with backend. That also counts. Yeah, obviously. Maybe some IoT. But in IoT space, we see some, I will list some cores, notable cores, that also can be used to build some kind of server hardware, or at least new IoT hardware is as performant as servers used to be like a decade ago. So in general, there are many acronyms. We'll try to solve a puzzle to understand a few of them. The ARM itself is the name of a company, and this company builds some designs and devices that I've already mentioned are so widespread that in this year, it's like 250 billion devices with ARM chips on this planet. And this is a huge number, and it used to be a huge number just a few years ago, but it grew in an order of magnitude. So another acronym here is ISA, Instruction Set Architecture. This is a language that we speak as developers, or our software compilers speak to the hardware to explain the task, the actual problem that this hardware must solve and give us some outcome, right? That's how computers work in theory and in practice. There is some low-level language, and we must compile and prepare our runtimes or our AUT-compiled programs to run on such hardware. And this is a new logo, right? This is in small letters, but it's still ARM. And in that ISA architecture, there are different versions of specification for the architecture. And they are called ARM v some major version, dot some minor version, dash profile. And profile can be targeted to different types of devices. Like it can be a set of IoT devices or real-time devices, or, which is most interesting for us, application profile. We write applications, real stuff, right? Even if it's full stack. It's even more real, of course. So this application profile is a major profile where we can meet Java. We can implement a JVM for lower profiles or for real-time profiles, but this is not so common. So for us, just application profile is a major thing. And the exact instruction set for this profile, for this 64-bit variant of ARM, is called A64. Well, that's another acronym. And ER64 is the execution state of processors to execute that system of commands. Well, it's a funny name, but it is what it is. And this is also a name of the OpenJDK port for this architecture and this execution state and this, well, set of commands. You get it. But the same port in Linux is called ARM64, just to let you know. So then different vendors create ARM hardware, and that are really different vendors with the same instruction set architecture. They are compatible processors, but produced by different manufacturers, designed by different vendors, but that vendors license the architecture from ARM. They also can license some implementation details, and there are different levels of such license. It is not free. So unlike RISC-V, for example, even if you just implement the instruction set, you have to get a license. For some devices, there are free licenses, or for some organizations, but this is not typically the case with like server hardware vendors that we discussed today. So that's a picture for profiles, right? We like that powerful hardware, which is right top, right, on this list. And here are two versions of the spec. One version is for 32-bit, it is V7, and the first version for 64-bit is V8. And this is a major version, and we'll see how it changed through time later. Our dimension profiles. And one interesting thing that we can find in typically in mobile phones or in some edge devices is a combination of totally different cores, ARM cores. They can even operate in different modes, and it's called big. LITTLE. Then we combine multiple cores, like here it can be like 3 different types of cores, all following or implementing the latest version of the spec, but they work together in a single chip. Unfortunately, Java knows nothing about that. Or mostly, like Android also doesn't care. So it's managed by, or I mean, Android runtime. So it's managed by the operating system, how you schedule your tasks inside such a device or whatever. There are many applications that we saw previously, great devices. I can't see it, but I hope that you can. There's a Raspberry, and Raspberry Pi, of course, is an important milestone across all the devices that regular developers are able to use to prototype or build some, well, cool systems for automation, for using Java to blink your LEDs or whatever. So it's cool. We have a lot of them in the company, and we sometimes work and connect them remotely if it's not graphical. If it's graphical, we use it locally. It's funny, you can run JavaFX on Raspberry Pi and it will have hardware acceleration, or you can build a native image and run it there. It works. And particularly that device and other devices can operate in different execution states, execution modes. It can be ER32 or ER64. And this port is still valid, it's supported, and by the way, mostly supported by our company. Well, it's an interesting outcome. So still it's available for, with newest Java versions, like Java 20 and upcoming Java 21. And with any of the ports, you can create a minimalistic runtime for your applications that are tied of disk memory or flash memory, wherever you put your code. Thickness, minimal VM or client VM to trade some performance for space. This is basically an embedded application. But still, let's get back to the real stuff, right? Something that can be used in high-end devices, desktops, servers, right? Or high-power edge devices. So here are some dates. That are release dates for certain versions of the specification. And here is RV8. And you see in each version there are some notable extensions. So every version brings some extensions that some of them are optional to implement, some of them are necessary to implement if you conform to that version. And what vendors typically do, they also implement some extensions from higher versions. So you already know the next spec and you can implement some extra. And useful extensions here are very different. Like here, for example, is BF16. This is a bfloat 16 support, right? This is for who attended previous talks. For machine learning. Or there are some crypto extensions to improve the speed of your encryption or decryption algorithms, or checksum calculation. Or an important response to what Intel does with AVX. Here is a vector extension called SVE, Scalable Vector Extension. And this one is interesting because in case of Intel, there are specified lengths for that vectors. And in case of ARM, the length is not specified, so it can be any length. And it's even possible to expect change of vectors length during runtime, or at least the device boot. So this is notable. And this allows to process complex data in a streaming fashion, for example. We have a lot of similar data, and we just process long streams of such data. And about that shapes with different features in spec revisions. There are notable hardware actually implementing that versions of the spec. So I started to work with A53 and Thunder X, which was a server class processor with 96 cores. Really weak cores, but implementing 64-bit spec, 64-bit cores, low TDP, and cheap processor time. So that is still a very important idea in this space, to have a lot of cores. They are now much more powerful, but still vendors put a lot of cores, especially for cloud machines. So they try to address a lot of memory, to put a lot of cores, to have what? How do you think? To split that to separate virtual instances and to sell it to you. Because you still have one person, one point of service, right? One rack or one unit, and it's easier to maintain. So that cores are really notable, and you can still meet them. Like A53 is still in many consumer products, A73 as well, A72. And then it was followed by Thunder X2, a real machine, a big iron, still powering a lot of supercomputer centers, implementing atomic instructions. Next version of spec, and yeah, I must say that every hardware here wasn't released the same year as the spec it implements, right? There is like 3 years gap between the spec is released and the actual hardware is released. This is quite normal, right? Because we first finalize the spec, then we finalize the actual product, the hardware, fix all the bugs. It's very similar to what happens in software. Hardware development also consists of a lot of bugs. Well, notable hardware here is A64FX. Who knows what it is? So this is the most powerful Japanese supercomputer by Fujitsu. And they designed a custom CPU for that. They also designed some custom interconnect and whatever. And it implements that scalable vector extensions, and it exists for a few years now. And it's ARM-based. Also some mobile cores, and that Neoverse. That's actually Neoverse with different letters and numbers represent families of design provided by ARM. So ARM prepares a design and then licenses this design to different vendors. Their hardware is somehow similar because it shares the same design, and there are different generations, and newer and newer versions of spec are implemented. So multiple actual CPUs hide behind these Neoverse letters. We'll see some products here. M1, right? Very notable processor. And just yesterday, we saw M2 Ultra, a new CPU by Apple. I think it's still in the same category as just a simple M2, because they just extended GPU options, the number of cores, and the number of neural processing units, but still it's about the same. And Ampere 1, the one that was released only like 3 weeks ago, a new processor by Ampere. This is a custom design, not a Neoverse anymore, and we'll just see some specs later. And there's now a very, very recent version, which might be 8.8 probably, but it became version 9, so it's still 64-bit, the same inheritance, but it's now called ARM v9. This is the newest version of spec, and there is already modern hardware that follows that version. You see some Neoverse. Again, it's a family of products. There are Cortex cores that you can already find in some desktop chipsets. I will show some products. So yeah, sorry. So different vendors, we know them. And of course, not all of them are on this picture, and we have more and more vendors each year. So this ecosystem grows from hardware perspective and from the software perspective, obviously. You see what Neoverse brings to hardware vendors and their consumers, us. It brings some predictability, so you know how to plan what hardware to expect next years. So we already have all of these, but this new generation is, well, very interesting. So you can really touch the hardware. You can go to a data center, or you can buy a server built by some of vendors. So that's not true for all different CPUs. Not all of them are freely available in consumer products. But for some of them, it is true. And it was very unusual in 2019. Then I touched it. So I had to go in faraway country and to see the actual hardware we worked with previously, and we worked only remotely. And it had almost 256 threads, so some of course were just broken here. And it looked like this just 4 years ago. Now that's a motherboard with 2 Ampere 1 CPUs. So it's like 192 CPUs in this motherboard. Less than on previous picture, but the overall computing power is higher. So 4 years later, and it looks cool, right? It has all that extension cards. It has all that DDR5 memory. Well, it's really powerful. And on that powerful iron, you run some software. And we like that stacks of software stacks, right? We are used to Java stack. We need JVM. OpenJDK is listed here, of course. But that OpenJDK runs where? Probably on Linux or Windows. Who runs OpenJDK on Windows? Be honest. I'm not sure. So this laptop is Ubuntu, but I have another one with Linux and another one with macOS. So well, how it happens in software world? People do implement optimizations. People do implement ports. So OpenJDK port exists now for several years. OpenJDK port for 64-bit ARM machines. And we have enhanced, Bellsoft enhanced this port with more effective or new intrinsic implementations for built-in JDK functions to improve performance. That was the main goal. And if we talk about performance, we think about measuring that performance, right? So you can run benchmarks, then they will show us something. And even for benchmarks, we sometimes need special holes in JDK or special holes in JVM. For example, if you use Java micro-benchmarking harness, it contains certain hooks. It uses certain hooks in JVM to trick compilers and to get you less biased results. And the same is true for other tools. They work nowadays. It required some effort. Like here are pictures from Async Profiler and JFR. So if you analyze the work of your application, your performance, what events do you have during the lifetime of your program? It's all possible. Works as usual. This is the main point. The hardware works as usual. The unit is replaced in a rack. The software works as usual. You just take your jar, you deploy it, or you build a container, more on that later, and it works or it breaks. Because sometimes programmers are not ideal. Well, people are not perfect. Let's replace people by machines. They will write even more stupid code. So here we have a code that does incorrect publishing of some data. And it's written in Java. And this code never shows incorrect results like the one listed on the top. It never shows incorrect results on x86. And this is a special test from a test suite called JC Stress that checks the correctness of JVM itself against different patterns that you can imagine with your Java programs in terms of concurrency. So this result of this program being incorrect, this observation, can be met on ARM hardware because it is not a so-called TSO model hardware. So it's highly out of order. And we actually can observe rare events with incorrect outputs from such a program. Which is scary, right? Because it is an event, one of a million or one of 1,000 executions is incorrect. This is a concurrency bug. The JVM itself is correct. The CPU is correct. Just our program is a kind of tricky. And it worked on x86. But don't be scared, just write correct programs. That's so easy. And why do we need to execute them on such a scary hardware? Well, because it offers us good performance and good price. So that's the main, well, advantage of using it, of migrating to ARM. We can save something. We can save power consumption. We can save our money spent for the cloud. And even that hardware can combine traditional classical computing and, for example, GPU computing, right? Obviously, there's a leader in such hardware, and that leader even releases a combined thing called NVIDIA Grace. And there are also 192 cores accompanied with some GPU processing, of course. So that's for HPC. We don't typically run hybrid workloads with Java. Well, we do, but it's not so common. So let's get back to server hardware. One family of products that we can meet in data centers, in different clouds, or we can buy consumer products, real blades or unit or two-unit servers with such processors. Ampere Ultra, Ultra Max, which has more cores, and Ampere 1. So in the topmost right corner, these are some not so old specs. On the picture, that are old specs. So things developed really quickly. And with an asterisk, there's the newest specs, only 3 weeks old. So they announced this CPU in the end of 2022, and they have just released it. And if you have a rack of such servers, you can run more than 7,000 virtual machines. Not JVMs, but real kind of VMware virtual machines. So it addresses a lot of memory, and yeah, it's a very powerful CPU. And you see, the newer CPU is, the newer version of spec it implements. Another family of products called Graviton. And yeah, if you go to Oracle Cloud, or if you go to Azure, these are machines that you get, Ultras. Currently, it's probably Ultra Max mostly. I would expect Ampere 1 as well. And there are other clouds and other ARM hardware in that clouds. And AWS has its own implementation, their own processor, now 3 generations of Graviton. And even the first generation is retired nowadays, so you can't create an instance on Graviton 1, and it just happened like last year. So you see, each generation takes a few years to implement. Each generation follows newer version of spec, and there are also a few years between spec versions. Each of them is produced on newer and newer factory settings. And you see larger caches, newer memory or wider memory access to cover typical performance bottlenecks. The frequency of that CPUs stays about the same, right? Because we're in the same data center, in the same rack, and physics is the same. But the kind of estimated performance, it grew like 10 times over just 5 years. That's, this number is probably a total lie. This is just an estimation, but we'll see some real benchmarks. And we are at the Java conference, so we will run some Java workloads. So Amazon claims that the last generation is like 25% better than previous one. Well, we'll see what happens. Just run some workloads and compare Graviton 3 and Graviton 2 on some reduced number of cores. This is not totally an honest comparison, but it shows us something. You see, really, you can see even an improvement over than 30% by just updating to a newer generation from M6G to C7 or whatever it is called. From another hand, who still runs Java 8 in production? Thank you. Well, if you need support for your distribution, you know, the point of contact. So yes, Java 8 is rarely updated, and there are no such good optimizations in the ARM port. And even Java 11 is not as well optimized as Java 17, and especially Java 20 and 21, which is like to be released soon, right? So if we update to a newer Java, we also get like 15, 20% improvement. So if we combine that improvements, we will have like 50% improvement. Don't trust me, of course. Run your own benchmarks. But this is the picture. It's just a random selection. We'll use the same benchmarks for another purpose later. So that hardware is AWS only, and this is current generation, well, not current, but Graviton 2 is Neoverse. Well, and Graviton 3 as well, but it's a new one, so it's really powerful. And Graviton 2 is very much like Ampere Altra. They behave similarly. We saw some micro-architectural effects that show us very similar pictures in different optimizations in benchmarks, but yeah, they're still different. So what about other clouds, like Google, for example? There are rumors, not verified, that they are also going to have it. Well, why all clouds want to have this hardware? As I said, because of cost savings. It's easier to manage it, and it really gives you some cost benefits. So this article called x86 Massacre compared price of some fixed workloads on modern x86 at that time and that new Graviton 2 at that time. And there was an impressive difference. It was so much cheaper to run the same work on that ARM hardware. And I believe it is still true for many workloads, not for all of them. There are, of course, ones where, well, Intel beats ARM very heavily. But in general, you have options. You can compare. You can create similar cloud instances and run your own workloads, your own benchmarks. And based on that, different clouds, they observe the growth of the share of using ARM instances by their clients, and they expect it to be much higher, like this year, 8%, right? Some estimation, probably from Amazon, and it will continue to grow. And Alibaba says, okay, we are going to move our services to our ARM instances, and it will be like a quarter of services till 2025. And most of such workloads, they run Java, right? We execute JVM and we calculate, and well, what's that? That's a fan. And we have been talking about different server hardware, but what about desktops? I don't like the noise of fan in my laptop. So you don't need a fan. You're going to have more computing power even in your Googles. Actually, that we saw again yesterday, M2 chip and some device that you put on your head. A lot of processing power and no fan. You couldn't imagine that, well, just a few years ago, because that was an essential part of your hardware. You have to deal with all that extra heat for nothing, I don't know, go to Norway or wherever. So this is a cold hardware, and it runs macOS. And what about Java? We will see it later. But that's not the only one, right? What about black laptops? I have one, and this is so reliable. It's not gold, so I can take it wherever I go, and put some sand on top of it. So, same vendor sells us an ARM-based one. So this is a real machine. It is more powerful than my current laptop. And well, it runs Linux, or it can run Windows. They're both optimized. That operating systems work on ARM. They show me a nice graphical interface. Or you can use even a laptop or even a tablet with some keyboard. And this tablet is powerful enough to run Windows on ARM and still to be responsible for pressing some keys. Or maybe not, because they removed the keyboard. But we even use such tablets in testing of JDK. Really? They're powerful enough. But I would buy this one. This one is cool. But I already bought this one, because it's even cooler. All right. So how do we run Java on all that operating systems? We need to port OpenJDK. Well, it's not that easy. First port was Linux port. And surprisingly, Microsoft participated not just in Windows port, right? It's Windows on ARM, not on x86, but also in macOS port. So Microsoft helps Java to work on Macs with ARM chips. Well, yes. And they have that ARM service in their cloud. Where's Windows? So you can run basically run your Java applications in any familiar environment. It all works. But it took some time and a lot of effort. You can even use graphics there. So AWT, Swing, JavaFX, no problem. You just get a build of your OpenJDK that supports it. It all works. And Swing and AWT are still kind of mandatory, so they're part of TCK, so you have to support it if you release compliant Java version. So even native images can be created for this architecture. So this is supported along with x86. Only 2 of them actually are primary targets. But why do we need that native version of your JDK, of your JVM to run some workloads? Let's look at the very same benchmarks. And we compared x86 build of OpenJDK. This is x86 Liberica, running in emulation using Rosetta 2 on Apple Silicon. This was M1 powered, probably Mac Mini. So it had a fan. Does Mac Mini have a fan? No, remember, it's silent anyway. And a native version of Liberica, specially built for Apple Silicon. And you see the difference. It's like it can be 2 times more performant if you run it in a native mode. And remember that Rosetta would be deprecated in a few years, I guess, right? Because after the end of transition period. So we know that ARM is different, and porting is hard. And you don't have to support everything that OpenJDK has inside to say that this port is complete. Like ZGC was implemented a few years after the port has been announced, even for Linux. And there are other projects that try to follow and to support ARM from the very beginning. Like Panama is an ongoing project. Vector API is an ongoing project. You can just use the API, and it's there. It's in the JDK on any platform. But you will probably fall back to a default, which is kind of slow Java implementation, if you don't have special intrinsic support for vectors on a certain architecture. And this support exists for ARM. So you can process your data in CMD way, and it will work fast. And it's also true, for example, for Alpine support, for musl. So we our company implemented that support in OpenJDK, and we supported ARM from the very beginning. So there are such builds. And some extensions or some features of the instruction set that become available in later versions help a lot runtimes like Java. Here is an example of using advanced atomics, and that gives like 5% better latency in your GC bound workloads. But what do we do with our applications, with our JVMs, all that configuration data? We put them in a container, and we must run that container. We expect it to work, but it also wasn't free from the very beginning because it required to build developer tools and working port of Docker and other technologies in the ecosystem of ARM hardware. And we can still create containers in different ways. Well, one of them is build packs. As far as I know, there is still no build pack for ARM 64-bit. It's a shame. But you can use different means of doing that. So as I mentioned, musl support is there. So you can take like Alpine Linux, for example, or Alpaca and create your container with a native runtime built for musl. So the resultant image will still be small on ARM architecture as well, just like on x86. It's so easy to create, but then you develop such a container. There are important cases, and it's natural to develop on the same architecture. Like if you use Apple Silicon, you work in ARM environment, so it's natural to create images for ARM servers. Or you use that Lenovo, right? But if you run on macOS, you have kind of slightly emulated hardware, so it's not exactly the same processor, but it's still interesting. Just check it. How do you see it from your container environment? So as I mentioned, you can just write a Docker file, create a container using the same ISA on your development machine or your CI as you have in production, and to deploy it. But you also can cross-build. So you can build x86 containers on ARM hardware and vice versa. That's a new way called build-X. So you specify the target platform. So here it's Linux AMD 64, and we run on Apple Silicon here, right? So we create x86 container, which we can deploy on x86 instance on ARM Silicon, or on Apple Silicon, on ARM machine. So this is easy, right? It's possible. Who uses Docker desktop? Who pays for it? Ah, okay. Okay, some conclusions. Hardware really works. It's so simple to rent a cheap ARM instance. You can get a small one, or you can get a bare metal one in a cloud, or you can buy a unit, or you can buy a desktop class hardware, or you can buy a Raspberry Pi for, debug. It will be the same port of OpenJDK, and it works there. And it's optimized for all the devices. What we as vendors and other companies who develop this port, what we do is we test on different CPUs, different up-to-date actual CPUs, then we perform some optimizations in the port. So it's an interesting task because sometimes results are very controversial. What helps one implementation doesn't help or hurts another one. But you as a Java developer shouldn't bother. You just create your jar file, put it into a container image, and deploy it. And it works. So thank you. Try ARM images. Ask me questions online, or I'm expecting some questions right now. Thank you. Yeah.
I have a question related to, for example, if we have specifically AWS languages, in your point of view, it's most interesting to invest time in named images or just use the regular Java in ARM?
For lambdas, probably native images are more efficient because they are designed to serve your short-living requests, and you shouldn't spend your time in warming up JVM. So you write something simple, well, please spend some time, compile it to native code, and just have an instant startup in lambdas, for sure. Yeah. But I'm not sure if lambdas are on gravitons. Need to check that. Yeah, okay, great. Yeah. So is it cheaper than x86? Okay, I haven't paid this person, but you see the point. Yeah, thank you. That's good to know. Yeah, let's have more questions. Or I will show the command line. I have it. So anyone is using Ultras in any cloud, like Azure? I know that Ultras are not in every region in Azure, but probably that's not a problem. No, okay. Yeah.
I have a question. You mentioned the JDK ports. This means that the JDK is developed for x86, and then it is ported to be compatible with ARM?
Yeah, so ARM was absolutely not the first port to a different architecture. Historically, Hotspot JVM started for Windows and x86. Then we know that Linux x86 is the x86 64 is the major port. But already other ports existed before that, like S360, for example, or it was ARM32-bit, or so-called unified port at that time, implemented by Oracle. So different architectures. And there's also an option, if you have a native compiler like CC, you can get a slow but compatible Java runtime called Zero. So it won't use any assembly hooks. It will just use plain implementation. So yes, it was just about 2013, maybe 14. Then, yeah.
My question is more about the newer Java version. So the 21 is coming in September.
Yeah.
And will it be available on ARM, or will it?
Yeah, it definitely will be available for ARM from the very first day. Like Liberica has, for example, the most number of different targets that we support. And besides of Linux x86, Linux AR64 is a primary target, for sure. Yeah, it's a good question. Like, what happens when JDK is released, right? Yeah, many vendors do the same, probably like all vendors. I don't know if someone supports only x86, well, maybe yes, but like Red Hat does the same, yeah.
I think OpenJDK by itself releases a lot of these binaries, which includes R64, X64, things like this. So I think at least the standard model you can get right now.
That's a good point. There's no such distribution called OpenJDK. There's no a single canonical binary. No. Yeah, right. That's Oracle OpenJDK. So.
It is, but it doesn't have the same licensing terms as Oracle JDK. Which is very fishy, as we all know, and we want to stay away from that. But if you OpenJDK.net, it's totally fine. It's GDL.
Okay, yeah, that's. I like this topic, but this is a bit aside of ARM. So. Yeah, but just remember, yeah, it's not a problem to get builds, to get container images. all that. Yeah. Yeah, thanks again.